Hi, I'm Josh Dodge, and today we're going to be looking at uncommon uses of synthetic division. And we're going to look at some very interesting zeros today. And this is the first uncommon use I'm going to show in this series. So let's review. We looked at negative digits, we looked at Vedic division, we looked at polynomial synthetic division and how that led to both Vedic division and polynomial synthetic division led to numerical synthetic division. We looked at some examples in previous videos. So in this video, in the next one, we're going to look at uncommon uses. Here is the typical uses of synthetic division while dividing a polynomial by a binomial in the form of x minus c. We looked at how that is, you can do more with synthetic division. Another property or another theorem is evaluating a polynomial and also finding rational roots of a polynomial. The last two, or these three are what's common in a typical algebra book. So we're going to look at some uncommon uses. In one of the previous videos, I showed how if I reveal the terms, you can remove and replace. And this is going to be very important for things that have different patterns. So in this video, we're going to verify some interesting zeros of polynomials. In the next video, we'll look at how to use synthetic division with multivariance polynomials. All right, so here's an example of using irrational with irrational zeros. So we can check if 1 plus or minus the square root are zeros. Now, the way that we can check here is usually zeros are in the form of conjugates. And here is no surprise. So we can do x minus 1 minus a negative, which would be a plus, square root of 5. So what we can do is multiply the two conjugates together, x minus 1 minus square root of 5. Now I can rewrite this as x minus 1, x minus 1. So I have a difference of squares. So it'd be x minus 1 parentheses squared minus the square root of 5 squared, which is 5. I can simplify this. So this would be x squared. Multiply these and then double it. So it's minus 2x plus 1 minus 5 plus 1 minus 5. And then I can simplify that as x squared minus 2x minus 4. And what should happen when I divide? So I have 2, negative 5, negative 6, 4. Set up my synthetic division, set up the bars, set up the remainder box. Leading coefficient is 1, so I don't have to write it. Remember, change the signs, so that would be 2 and then 4. Bring down the 2. Multiply at the diagonal, so that would be 4 and then 8. Add the column, so negative 5 plus 4 is negative 1. Multiply at the diagonal, so it's negative 1 times 2, which is negative 2, negative 4. Add the columns, 0, 0. And since the remainder is 0, that means that those are zeros. So we can do it this way. This is kind of familiar, but we can also do it another way. We can just check the zeros. Now, when we're checking the zeros, so we'll have 2, -5. Let me put those terms in there, x squared. We might have a 0 square root of 5x squared. We may or not need these. -6x 0 square root of 5x, and then we have 4, and then 0 times square root of 5. These are just zeros, but I have this square root of 5 in here, so it's going to do some weird things. Now we have our remainder of 2. Now, what we're going to do is take the, this is x minus 1 minus square root of 5. That's what I would divide it by. That's changing the signs, but notice that when I change them here, they're going to become the same. They're going to become positive. So 1 over x. So bring down to x squared. We're going to divide by 2x cubed. We're going to divide by x, so it gives us 2x squared. We're going to multiply at the diagonal. So this would be 2x squared, and then 2 square root of 5x squared. Add the column, right? We're going to add this column. -5x squared plus 2x squared is -3x squared. Divide by x. So that is -3x. Now multiply at the diagonal, and notice that it's going to take a leap. So this would be -3x. Then I have -3x times this, so it'd be -3 square root of 5x. Now I'm going to multiply or add the next column. So that would be 2 square root of 5x squared divided by x, which is 2 square root of 5x. Now multiply at the diagonal. So when I do that, 2 square root of 5x, and then 2 square root of 5 times square root of 5. So multiplying this times this, which would give me 2 times 5, which is 10. So, and that's a 10x. So you see how it reverses like that, an x, and that's perfectly fine. Then we're going to add the column. So that would be -9 plus 10 is 1, or 10 minus 9, which is 1x, which is just 1. You notice I get 1 square root of 5 like that. Add the next column. So the next column is -1 square root of 5x, which gives us -1 square root of 5, right? Just dividing that x off. Multiply at the diagonal, right? So I'm multiplying these two. I'm multiplying these two times this. So 1 times negative square root of 5 is -1 square root of 5, or just negative square root of 5. And then negative square root of 5 times square root of 5 is -5. Add the columns. 4 minus 5 is -1 plus 1 is 0. And then that last column there, square root of 5 minus square root of 5 is 0. So it checks out. All right, let's look at the next one. Now we're looking at a complex 0, or a complex number, and we're going to see if it's a 0. So again, I'm going to expand it, and then the way that I'm going to expand it is x squared. And the same thing as before, so 4x 0 I x 13 and then 0 I. And then put it in the remainder box. Now on the side here, I'm going to put where I put my irrational number, complex number before, so -2. And this is 1 over x. So we're going to bring down that x squared. So that's just x multiply the top part. So that'd be -2x. And then 3ix. Next, add the column. So 4x minus 2x is 2x. Gives us 2. Add the column. So that would be -4. -4 jumps. So you have -4. And then 6i. Add the column. Next column. So 0i plus 3ix is 3ix. Divide by x, which is 3i. Multiply these two and put them in the according diagonal. So 3i times -2 is -6i. And then 3i times 3i is -9. So once you get to the remainder box, just add those two columns. 13 minus 9 minus 4 is 0. 0i plus 6i minus 6i gives us 0. So that checks out since the remainder is 0, and that is it. So it is a solution. So anytime you have a remainder that is 0, no matter what it is, complex, rational, irrational, whatever, it's a solution. Check out my article and sources below. In the next video, we're going to look at the division of multivariate polynomials. Polynomials with both x's and y's, and I'm going to show you how to do that with synthetic division.